Okay, so we're gonna get started with Chatellier's principle. I don't like speaking French, and I'm pretty sure I'm pronouncing that wrong. So I call it Le Chandelier's principle, which is why there's a picture of a chandelier there. You guys can call it that if you want, or you guys can look up the correct pronunciation. Anyway, Le Chatelier's principle, the chandelier principle, basically tells us if there is a change in temperature, pressure, or concentration, the system will shift its equilibrium. So equilibrium changes if temperature, pressure, and concentration changes. That's basically what it's telling us. Okay. So the chandelier principle tells us if you change the temperature, the pressure, or the concentration of something, the equilibrium will also shift. Okay. Maybe. Maybe it will, maybe it won't. This class is all a mystery. I told you guys, I'm just making this up as I go. Okay. So down here, I have this big little graphic for you guys to look at, but let me just explain it very simply for you guys, okay? So when we have let's say we have a reaction like this. We got reactants on one side and we got products on the other side, okay? Let's just say, for example, and then they're going to be at equilibrium, sorry. Okay. So let's talk about temperature first. So let's say, for example, let's say that we are at equilibrium, okay? We're at equilibrium, we're good. What is it? The rates are the same forward and backwards. Let's just say, for example, that the reactants are typically at a lower temperature and the products are at a higher temperature, okay? Let's just say, it doesn't matter if it's like this, it could be the other way around, but let's just say this is how it is. The reactants are typically at a lower temperature, products are at a higher temperature, okay? And this is your system. If we increase the temperature of the entire system, what's going to happen is it's going to have a reverse effect on equilibrium. So since products are typically at higher temperature, if you increase the temperature of the whole system, the equilibrium is going to move towards the reactants, the opposite effect. Does that make sense? So if the products are typically the ones with higher temperature and you increase the temperature of the whole thing, equilibrium is going to shift to the other side so it can kind of balance out the change that you made. Okay, that's why I kind of like saying it's a chandelier, because it swings like a chandelier. Okay, never mind. I'm not going to sing the song, but yeah. And the reverse effect is going to happen if you lower the temperature. You see how the reactants are at a lower temperature? So if you lower the temperature of the whole system, the equilibrium is going to shift to the side that has the higher temperature. Okay, and the reason why we do this is the reason why this happens is so that it can balance out the change in the system. Okay. Make sense? Okay, so basically it just goes to the opposite. It has the opposite change on equilibrium. Okay, the same thing can happen with pressure as well. Okay, so let's say the reactants, and this is typically with gases, but let's say the reactants have a lower pressure and the products have a higher pressure. If I decrease the pressure, is it going to shift to the left or to the right? The right, yeah, it's going to have the opposite effect. Okay. So if we decrease the pressure, it's going to shift to the side that has higher pressure. And then the same thing is true if we do it the other way. If I increase the pressure, which side is it going to shift to? The left. Yeah. Okay, so that's what the chandelier principle tells us. It tells us that if we change the system, it's going to have the opposite effect on the equilibrium. Okay. Okay. And the last thing that we're going to talk about is the concentration. And this is kind of, I think this is the more obvious one. Let's say if we increase the concentration of the reactants, what's going to happen during equilibrium is it's going to shift to the products. So it just has the opposite effect. If you increase the reactant, excuse me, it's going to shift to the products. And then if you decrease the concentration of the reactants, it's going to swing towards the reactants. Okay, so it basically just has the opposite effect of what you do to the system. All right. Any questions about the Chandelier principle? Make sense? Now, do you guys remember when I told you earlier about one of my favorite reactions? N2 plus H2 makes NH3, the one that fed all of Europe and then killed a bunch of people because they made ammonium out of it. Now, this is the way that they did this was through the Chandelier principle. Okay, so we have ammonia, which is what we can use to make fertilizers and to make nasty toxic gases, right? Let's say that you are a scientist. We'll say a fertilizer scientist because we don't want to say a toxic gas scientist, but you're a fertilizer scientist and you want to grow more food. You need ammonia to make the food, okay? Okay, but when you create this the system, it comes to equilibrium, but you want more ammonia. What can you do to make more of the product? Yeah, so what's going to happen, what you want to do is if you increase the concentration of N2, and if you increase the concentration of H2 in your system, what's going to happen is it's going to force the equilibrium towards the product. And that's how you can create more and more ammonia. You just need to add more and more of the reactants, okay? So that's how this principle works. You just need to alter one side and it'll have the opposite effect on the other side, okay? And even if you didn't have if you didn't want to add more of this, another way that you can do it is, hold on, let me do the stoichiometry for this. Okay, if you guys notice, this side is going to have a higher pressure normally because you see how there's 4 moles of gas, right? And then this only has 2 moles of gas. So this side is high pressure and this side is low pressure. If I want to swing it towards the products, what could I do to this system to create more ammonia gas? Yeah, if I increase the pressure of the system, you can create more ammonia gas. So even if you didn't have more nitrogen and hydrogen gas, if you compress the system, if you make the volume smaller, it would automatically create more ammonia, even if you didn't add more of the reactants. So a lot of smart ways to make fertilizers and toxic gas. Okay. Don't try this at home though.
I heard a story that one time, apparently there's these students who were working on like a science project, and they accidentally made mustard gas.
Yeah, it's actually pretty easy.
Oh, okay.
Yes, by accident. That's why you don't mix chemicals randomly. All right, you guys ready to move on? Okay, so that's the Chandelier principle. Okay, and all this right here is just an explanation of what I was telling you guys, okay? Let's move on. Okay, let's do this one. I want you guys to do 12.30. So what happens to the equilibrium of this reaction right here if the volume is increased? So if you have this equilibrium right here and you increase the volume, what's gonna happen? Think about the Chandelier principle we just talked about. I'll give you guys a minute to finish that up. Alrighty, guys, let's go over this one. So if you guys notice here, you'll see that there are 3 moles of gas on the reactant side, and then there are 2 moles of gas on the product side, right? So if I increase the volume of the system, what happens to the pressure? Yeah, the pressure is going to decrease, okay? If I decrease the pressure, okay, let's take a look at this. So if there's more moles of gas on the reactant side, which side is going to have the higher pressure? the left side is going to have the higher pressure. Okay, so if I decrease the pressure, which side is it going to swing towards? Yeah, it's going to swing towards the reactants, because if I decrease the pressure, it wants to balance that out by increasing the pressure. And you can increase the pressure by swinging towards the reactants because there's more moles on the left side. Okay, so if we wanted to communicate that, what you would say is that, what is it? The pressure is higher on the reactant side because there are 3 moles of gas compared to the product side, which has 2 moles of gas. Okay. And then you can say increasing the volume will decrease the pressure, and then which causing the system to, or causing the equilibrium to shift to the reactant side because it has higher pressure. Something like that. Okay, so basically you just need to point out 2 things. You want to point out that the reactant side has a higher pressure because it has more moles of gas. And then you want to point out that increasing the volume will decrease the pressure. And so the Chandelier principle tells us it's going to have the, it'll shift to the opposite side. And so it'll go to the reactants. Okay. And just a reminder again, when you guys are writing your explanation for FRQs, don't humanize these atoms and things like that. They don't have feelings. They don't like anything. They don't want to do anything. They don't have intention. They just kind of do things. I'm sorry if that hurts your feelings, if you've gotten attached to these molecules. I have a fond attachment for caffeine. Yeah, I humanize caffeine. All right, any questions? You guys ready to move on? Okay, so we're going to talk about some of the implications of the Chandelier principle now. So we've talked about how to use it. I think you guys have an understanding of what it does to reactions. Now, we just talked about how pressure, right? Pressure will affect the equilibrium. And so we had our nice example, one of my favorite reactions right here. We have 4 moles of gas on the left side, 2 on the right side. So increasing the pressure will shift the reaction to the products, okay? But let's look at an example where we have the same number of moles of gas on the left and right. We have one right here. Okay, why is there an E? Okay. So if you guys notice here, there are 2 moles of gas on the left side and 2 moles of gas on the right side, right? Okay, so if that is the case, changing the pressure does not affect the equilibrium, okay? So if you're not going to be changing the number of, or if the number of moles on the left and right are the same, changing the pressure doesn't change equilibrium, because regardless of which side it goes, it's going to have the same amount of pressure. Okay, so again, if you have the same number of moles of gas for reactants and products, changing the pressure will not change the equilibrium. Okay. Any questions? Make sense? Okay, so I just wanted to point that out. Now there's some numerical calculation stuff, explanation that I wrote down here that you guys can take a look at. But basically it's just telling us why mathematically, if we change the pressure, the equilibrium is gonna end up changing. It's because we're gonna be changing the values here. If it no longer equals the equilibrium constant, things are gonna change until it reestablishes equilibrium. That's basically what it's telling us. You guys can take a look at this in your reading, which I know that you guys all do. according to the schedule. But I just kind of wrote down the explanation for the calculations. Yes, we are on chapter 15. Okay. Temperature change is another one that I want to talk about. So Chandelier's principle tells us that it's going to have the opposite effect with temperature. And so let's take a look at this equilibrium right here. We have this compound right here, COH2O6, and then we have cobalt-2 chloride, COCl2, okay? Now, depending on the temperature, this equilibrium is going to change, and for this system, it's actually going to end up changing color, okay? So this one right here on the left, the reactant is going to be a pale pink color, and this compound right here on the right is going to be a deep blue color, okay? And so if you guys take a look at the equilibrium, let's start with equilibrium. When there are the significant amounts of both reactants and product, the solution is going to be a violet color. So kind of a mix between pink and blue. And now if you guys take a look at the enthalpy, I know you guys haven't heard that term in a while. If enthalpy is greater than 0, is this a exothermic reaction or endothermic? So let's talk about this first. Is heat going to be a reactant or product? If enthalpy is greater than 0. Who thinks reactant? Who thinks product? Who's super confused? Okay, so let's talk about enthalpy. So if enthalpy is greater than 0, is heat released or is it absorbed? Yeah, it's absorbed. If enthalpy is greater than 0, heat is absorbed. Okay, because enthalpy is the energy inside the system, right? Okay, so this is your system, okay? And you have energy in here, okay? And this is your initial system. Okay, delta H means change in enthalpy, change in energy inside the system. So if the delta H is greater than 0, is it a positive change or negative change? Positive. If it's a positive change, did the energy go up or did it go down? Yeah, the energy is gonna go up. So if delta H is greater than 0, the energy of the system goes up. If the energy of the system goes up, is it absorbing heat or is it releasing heat? Yeah, it's absorbing heat. Okay, make sure you guys keep that in mind because we're actually going to go back into enthalpy in 2 units. So just make sure that you guys keep that in mind. I guess it was a good way for you guys to see how well you guys remember that. But yeah, so it's going to be absorbing heat. Okay. So if it is absorbing heat, is heat a reactant or is it a product? It's a reactant. Heat is going to be a reactant. Oh, Josh, you're like 0 for 10 right now. It's okay. It's okay. It's been, dude, we haven't talked about this in like 2 months. I think it was before break too. Okay, so heat is a reactant. Okay. So we have our equation right here. This is our system. Okay, so if I increase the heat in the system, which way is the reaction going to shift? Yeah, towards the product. Okay, so if we increase the heat, okay, it's gonna cause the equilibrium to shift towards the product because heat is a reactant. Okay, so we see it right here. So if we add heat, what's going to happen is it's going to swing towards the product, and then the color is going to change from equilibrium where it was purple, and it's going to turn blue right here. Make sure you're very careful with this because I know the Chandelier principle seems kind of easy, but then again, we start mixing it with things like enthalpy and it can get a bit confusing. Okay, so let's think about the other way. So if I decrease heat, so if I cool the system, what color is the system going to turn? Yeah, it's going to turn pink because it's going to shift towards the reactant. And so if we take a look at the picture, if we cool it down, it's going to shift towards this pink color. Pretty interesting. Okay, but just make sure that you guys are careful with enthalpy and things like that. It'll kind of trip you up if you don't know if it's a reactant or a product. Okay. Hopefully that was enough social trauma for you to remember. Okay, so just keep in mind, enthalpy, if it's greater than 0, heat is a reactant. If it is less than 0, it's going to be a product. All right, any questions about that one? Makes sense. So I have a little thing here if you guys want to look at it later on your own time when you're studying. But let's do 12.31. I want you guys to use the Chandelier principle and explain why equilibrium vapor pressure of a liquid increases with increasing temperature. Do you guys remember what vapor pressure is? Oh gosh, okay. Dude. Oh goodness. Okay, so vapor pressure is going to be if you have a closed system like this, and then you got a liquid down here. Okay, so when you have a liquid and then up here is a gas, so it's like open space, okay? Vapor pressure is the pressure that is caused because what happens is the liquid molecules, they vaporize, even if they're not being boiled or anything like that, they vaporize into gas molecules, okay? And that causes a pressure, okay? And that's what we call the vapor pressure. So the vapor pressure is the pressure that is created by a liquid becoming a vapor inside of a closed system. So this pressure that is caused by the liquid molecules turning into gas is going to be the vapor pressure. And this is an equilibrium because what happens is the liquid molecules turn into gas. So let's say, for example, we have H2O here. So if we have liquid water, or water is a liquid, and then water molecules, what's going to happen is they're going to turn into water vapor, into a gas. But what's going to happen is on the surface, some of the gas molecules are going to turn into a liquid. And then there's this equilibrium where some of them turn into gas, some of them turn into liquid, but they keep a consistent pressure. And that's what we call a vapor pressure. Okay. So knowing what vapor pressure is now, I want you guys to explain why the vapor pressure would increase if you increase the temperature. Okay. Just kind of think about it. Give you guys about a minute and a half to try that out. You can talk about it with the person next to you. See if you could write an explanation, and then we'll go over it together. Okay, let's go over the answer to this one. So what we first want to do is we want to identify what is going on, okay? So we understand what vapor pressure is, so let's try to explain why increasing the temperature will increase the vapor pressure, okay? So first thing that's kind of obvious that we can write down is that increasing the temperature will change the system, right? Okay, you guys don't need to write this part down. I'm just kind of stating the obvious, right? If you increase the temperature, it's going to change the system. Now, if increasing the temperature, what does it do to the liquid and the gas? Typically, if you increase the temperature, what do you get more of? Yeah, usually it's going to cause a shift towards the gas, right? So increasing temperature converts liquid to gas. Okay. Now, if the system is going to create more gas, so increasing the temperature converts liquid to gas. So what's going to happen is more gas will result in a higher vapor pressure, right? Because the more gas that you have, the higher the pressure is going to be. And so what we can deduce from that is that creating more gas will minimize the effect of increasing temperature. Okay. And then so from there, we can say that, therefore, increasing temperature increases vapor pressure. Okay. So basically, this is what's going on. So when we have a liquid, right? When you heat up a liquid, it's going to naturally want to turn into more gas, right? And so if there's more gas, there's going to be more vapor pressure. And so what happens is the liquid is naturally going to create more of the liquid is going to vaporize in order to prevent the change in temperature from making a bigger change, right? Because if the liquid didn't do anything, what would happen if you increase temperature? It would turn into a lot of gas, right? Right? You would turn the liquid into a gas. However, if the liquid naturally starts vaporizing, because it was already doing that, if it starts vaporizing more, what's going to happen is increasing the temperature will not cause more gas molecules to be made. And so what's going to happen is it's going to minimize the change on the system. You guys are looking at me like I'm crazy. Kind of? Okay, so let's do pictures. Okay, because I'm a great artist. Okay, so we said that naturally, when we have a liquid and gas, it's going to be an equilibrium, right? Some of the liquid molecules are going to turn into gas molecules, and the gas molecules turn into liquid molecules. Okay. Now, this is the part that I want you to concentrate on. This right here. The gas molecules turn into liquid as well. Okay. Now, if I increase the temperature of this system, okay, what's going to happen is you're going to want to create more, right? There's going to be more shift towards the gases, right? Okay. Now, what's going to happen is if you increase the temperature, the gases are not going to want to turn back into the liquid naturally, right? Because there's more energy in the system. And so this is the reason why vapor pressure increases. It increases because the liquid water is going to turn into water vapor, and the water vapor does not come back into the liquid form. And then that'll naturally cause the pressure inside this area to increase. And that's what we call vapor pressure. Okay, that's why. Makes a little more sense? My amazing drawings. It's too early to be talking about this, huh? Okay, but anyway.
Because the temperature increases, there will be more gas, but the pressure is like no.
Yeah, so it's not going to want to turn back into, it's still going to, but not a lot. It's going to be a very minimal amount of the gas molecules are going to turn back into the liquid molecules because it wants to maintain this relationship between liquid and gas. Because the other alternative is everything turned into gas, and that's a huge change on the system, and it wants to resist that change. Okay, so there's another explanation of that down here, which you guys can read if you want. And we're going to do our last problem today with the Chandelier principle. Okay, I'm going to give you guys 5 minutes to try this one out. So we have a reaction right here. We got the change in enthalpy. And there are five different things that could happen to this equilibrium. And I want you guys to tell me which direction the equilibrium will shift depending on these changes. Okay, try to write a short sentence explaining why. That'll kind of help you guys out for your understanding as well. We'll go over this one. We'll take a quick break, and then we are going to get into the last section of this unit, and we'll be done with unit 11. All right, guys, let's go over 12.32. So let's start with the first one. The first one should be pretty easy. So if I increase N to O4, which way will the equilibrium shift? To the products, right? Yeah, because N2O4 is a reactant. And so if I add more reactant, it's going to shift towards the products. So I'm just going to write that it's going to shift towards the right. Okay, that's going to be A. Super simple. All right, let's go to part B now. If I remove NO2, which direction is it going to shift? Who thinks to the left? Who thinks to the right? Yeah, it's going to be to the right. And it's because if I have less of this, if I have less product, I'm going to want to make more product. So it's going to shift to the right again. Okay. Now let's go to part C. If I increase N2, if I increase the pressure by adding N2, which direction do you think this is going to shift? Show me with your fingers. Point in the direction. So actually, this one was a trick question. There's actually going to be no change. And let me explain why. So if I increase N2, okay. Okay, so we have a system like this, right? We have N2O4, which has its own unique pressure. We have NO2, which has its unique pressure. If I put N2 in here, is that going to affect the pressure of these two gases? No, right? It's independent from one another. Remember partial pressures? They all have, or hopefully you guys remember partial pressures. They all have their own pressures. The total pressure is when we add them all up, but they have their own individual partial pressures. So if I add N2, it doesn't matter if I change the total pressure because I'm not changing the pressure of this guy and I'm not changing the pressure of this guy because N2 is not in equilibrium with these two compounds, right? N2 is just kind of its own thing. So there's actually going to be no change to the equilibrium. So that one was a trick question. Okay, does that make sense though? It's because N2 is not in equilibrium with these compounds. So no change because N2 is not in equilibrium with N2O4 and NO2. Does not change the equilibrium pressure. Okay, so it changes the total pressure, but it doesn't change the equilibrium pressure. Okay, and Chandelier's principle is talking about the equilibrium pressure, not the total. Okay. All right, let's go to part D. If volume is increased, okay, which direction is it going to shift? To the left or to the right? Okay, show me with your fingers. See, 2 fingers, 3 fingers, 4 fingers, 5, 6. Okay, yeah. So if volume is increased, let's think about this. If volume increases, what happens to the pressure? Pressure is going to decrease. Now, if you take a look at this equilibrium system right here, which side has more pressure, the left side or the right side? Yeah, the right side has more pressure because it has more moles of gas, right? There's more molecules of gas. So if I increase the volume, the pressure is going to decrease, which means the system is going to want to increase the pressure in order to balance it out. So here, the system, the equilibrium is going to shift to the right. Okay, it's going to shift to the right because it wants to minimize the change in pressure, equilibrium pressure. It's kind of confusing, huh? When you're like left, right, more or less. Kind of hard to keep track of all this. Yeah, it's been hard. Okay, and then lastly, let's go to the temperature. So if the temperature is decreased, we got to figure out what happens to equilibrium. Now, in order to talk about this, we need to take a look at the enthalpy. And we just did this, so I'm hoping y'all remember. So if you take a look at the change in enthalpy, it's a positive change, right? If it's positive, is heat a reactant or a product? Yeah, heat is going to be a reactant. Okay. So if the temperature decreases, is the system going to want to heat up or cool down? It wants to heat up. The system wants to heat up. How can the system heat up? By shifting to the left, because it'll have more energy in the system. Okay. So follow-up question. If the equilibrium is shifting, if you touch it, is it going to be hot or cold? So here, if you decrease the temperature, right, the equilibrium is going to shift to left. So if the equilibrium is changing and you touch it, is it going to be hot? Are you going to feel hot or cold when you touch it? It's going to feel cold because it's absorbing heat from the surroundings in order to heat up, because we just said it wants to heat up the system. How is it going to heat up? It's going to steal energy from you. It's going to steal your power. It's confusing, huh? Like I said, guys, I'm just making this up. I don't know if any of this is real. Yeah. D, E, oh, the last one, yeah. So first thing we need to look at is the enthalpy, right? The enthalpy is 58 kilojoules, which is a positive number, right? If it's a positive number, that means heat is a reactant, okay? And so if heat is a reactant, that means this side has more internal energy. It has a higher internal temperature, okay? And so if I decrease the temperature, right? If the temperature of the system goes down, Chandelier's principle tells us it wants to do the opposite to balance out the change, right? So if you cool the system down, the system is going to naturally increase its temperature in order to balance out that change. Okay, and then we talked about which side has more internal energy, the left side or the right side. The left side has more internal energy because that's the side where heat is, right? And so it's going to shift towards the left. It's because of the internal energy. All right, so you guys kind of look like you guys are wiped out. So we'll take a quick break. If you guys need to go to the restroom, you can go to the restroom. And then we'll go to the last topic and the last problem for this unit. Okay, let's take a break, guys. All right, so last thing we're going to talk about for this unit are catalysts. Okay, you guys might have heard that term before. We talked about it briefly during the previous unit. And you guys don't need to copy all this down. I'll tell you, there's only two really important things you guys need to know for catalyst. The first thing is that a catalyst, all it does is it lowers the activation barrier between reactants and products. Remember that energy barrier we talked about, the hill that it needs to go over? The only thing that a catalyst does is it makes that hill smaller. Okay? So catalyst, it lowers the activation barrier between reactants and products. So it just makes it easier for the reaction to happen. Okay? As a result, if you use a catalyst, the reaction gets to equilibrium faster, but it does not change what that equilibrium is. So it doesn't change the K value. It doesn't change the ratio between the reactants and products. It just makes the reaction get to equilibrium faster. Okay, that's what a catalyst does. Okay, that's it. That's what a catalyst is. And that's it. Congratulations, guys. That's unit 11. I'm not even joking. That's it. What? We have a problem. I know. I'm so okay. My bad, guys. I know you guys want more work, but that's all I'm gonna give you. No. Yeah, that's it for unit 11. Congratulations, guys. We'll do one problem afterwards. This is gonna be a big doozy where we combine everything. But that's all the information you'll need about equilibrium. Okay. So 2 things from this part right here. Catalyst lowers the activation barrier. And so catalysts, they help you get to equilibrium faster, but it does not change what the equilibrium is. Okay, it doesn't change that ratio. So that's what you guys can see here. It lowers the energy hill, it's the green one. But if you guys see right here, the position of equilibrium is the same. All righty. Ready to move on to the last problem? All right. Big problem. So let me ask you guys a quick question. Do you guys just want to try it on your own, or do you want me to kind of unpackage the problem for you? Help a little bit? Okay, I'll help a little bit. If you guys don't want help, just kind of ignore me. Just and then you guys will go over it, okay? So let's look at the scenario. So at temperatures near 800 degrees Celsius, steam is passed over hot coke, not Coca-Cola, but a form of carbon obtained from coal. Okay, and that reacts to form carbon monoxide and hydrogen gas. So you have the reaction right here. Okay. So solid carbon, water vapor produces carbon monoxide, H2O. H2. This is already balanced. Okay, so this mixture results in a fuel called water gas. Okay, so that's a scenario we're looking at. Okay, any questions about the scenario? It's just kind of primer information for the reaction right here. Okay, so at 800 degrees Celsius, the equilibrium constant is Kp equals 14.1. So the equilibrium constant for partial pressure is 14.1. Now, quick thing you guys want to notice is that this is Kp. Okay, so what unit of measurement are we going to be using for this problem? Yeah, you're looking for ATM since it's Kp. So if it's Kp, it's going to be for pressure. Okay, that means we're not using molarity. We're using atmospheres, ATM. Okay, it's one thing you want to kind of pull out right away. Now it's asking us, what are the equilibrium partial pressures for H2O, CO, H2 if we start with solid carbon, okay, and 0.1 moles of H2O in a 1 liter vessel. Okay, so here we're going to have to use an ice table. But before we go into the ice table, I want to give you guys a little bit of help. Okay, so I'm going to cover parts, the other parts. And we're going to create an ice table. So create an ice table with me, everybody. And then we'll get into it. So copy down your reaction. Oh, sorry. Copy down your reaction and then create your ice table. I'm going to be doing the same up here. Okay. So let's plug in the information that we have into our ice table. Now, we want to find the equilibrium partial pressures for H2O. So we want to find this value right here, CO and H2. So the values that we're looking for are these three on the bottom, okay? The equilibrium partial pressures. Now, it tells us that we start with solid carbon. So what number should I put here for carbon? Nothing, there's nothing. Why? Why do we have no number for carbon? It's a solid. Oh, I'm so proud. Yeah, carbon is a pure substance. And so we don't include it in our ice table. Okay, we don't include pure solids and pure liquids. Okay, which means the only value we need to put in is going to be H2O gas. Now, we said that the information that we need is pressure, right? So the number that we need is ATM. But the information that we have for H2O is all we have is 0.1 moles, 1 liter. Do you guys remember how to find pressure using this information? Oh, goodness. Okay. If you guys look at your notes and your equation sheet, you guys remember the ideal gas law, PV equals nRT? Vaguely, yeah, we did this in like, I think October or November, so it's been a while, but this is the equation that we use. Okay, so we're gonna be rearranging this equation. So we're gonna try to find the pressure of H2O. N is the number for moles. R is the constant, 0.0821. T is the temperature, and then we divide that by volume. Now we have all these numbers, including temperature. The temperature is equal to 800 degrees Celsius. But remember, we need to convert that into Kelvin. Okay, so plus 273. Okay, so I want you guys to use this information to find the pressure of H2O, which we're gonna put in right here. Okay, so I'm gonna give you guys some time to get started to calculate that out. If you are comfortable solving out the entire problem, go ahead and do so. And then after that, I'm gonna start going over. I'll give you the value for H2O in just a second, but try to calculate that out, okay? Yeah. .0821. Yeah, the R value, right? The gas constant. Yeah, I'll write that down right here. R is 0.0821. Yes. Something like this. We'll see how I feel. How kind I'm feeling the day I make the test. Alrighty, guys. So for the pressure of H2O gas, the initial pressure, you should have gotten 8.81 atm. So that's going to be your starting number for the atmosphere or for the ice table. And then from here, you're going to have to calculate the equilibrium. So I'll give you guys a few more minutes to solve that out. If you guys need a little help, it's going to be minus x plus x plus x. Alrighty, guys, I'm gonna start going over it. If you guys are finishing up your quadratic and your calculations, feel free to kind of ignore me and just finish up your calculations. So I finished the ice table. So 8.81 minus x for H2O and x for CO and H2 because you're going from 0 and you got to create some product. So if we use the Kp value of 14.1, we can get this equation right here. I got that using the equilibrium constant for partial pressure equation. And then if we simplify that out into a quadratic, we get x squared plus 14.1x minus 124.22 equals 0. Again, if at any point you have a question, let me know. And then we plug that into a quadratic. I'm not going to read that, but you get that. Make sure to use the Pop Goes the Weasel song. It'll help you remember. And then that should give you an answer of 6.14. With the other answer being a negative number, so we can't use that. Okay, so from there, very simple. We can just get the partial pressure for CO. So the equilibrium partial pressure for CO is going to be 6.14 atm. Same thing with H2, 6.14 atm. And then for H2O equilibrium, we just need to subtract that from 8.81. That'll give you 2.67 atm. Okay, there you go. That's going to be the answer to part A. Okay. If you got numbers very similar to that, that's fine, like 6.13, 6.68. Any questions, Chillin? Give you guys a couple seconds to copy this down. If you guys need the final answers, because we will need it for some of the following sections, and I'm going to erase this in just a second. So if you need to jot down anything that's different or that you want, you guys can jot it down. I hope this class is helping you guys in math a little bit too. Maybe. All right, let's move on to the next part, part B. So part B, what is the minimum amount of carbon required to achieve equilibrium under these conditions? And so basically we're trying to figure out how much carbon do we need in order to get to this equilibrium. Now, for this part, we're gonna need to use the stoichiometry, okay? So you guys can see that we have 1 mole of carbon for every 1 mole of everything else, right? Now we just found the partial pressures at equilibrium. The partial pressures at equilibrium are 2.67 atm and 6.14 atm for the products. Okay, and so what we can do now is we can use the PV equals nRT, the ideal gas law. And remember, N stands for moles, right? So if I can find the moles of either the product or the H2O, we can use that and the stoichiometry of this reaction to find out how much carbon we need. That makes sense? If it kind of makes sense to you, I'll let you guys go ahead and do the calculations, but I'm going to start going over it. So what you want to do is you want to rearrange this equation. So N, the moles is equals to PV divided by RT. Now, what we're trying to find is the amount of carbon that we need at equilibrium to get to equilibrium. Okay, so we're just going to use some simple stoichiometry. You can pick any one of these gases. It doesn't really matter. I'm going to choose H2 or H2O, sorry, because that's the first one. So we'll just pick H2. So H2O, the moles of H2O is going to equal to the pressure. The pressure of H2O is going to be 2.67 atm. The volume right now is 1 liter. Next, we're going to put in the R value, which is 0.0821. And then for the temperature, sorry, what was the temperature again? 1073 Kelvin. Okay. So what we're going to do now is we are going to calculate this out. And if you simplify this value right here, sorry, let me grab my calculator. 2.67 divided by 0.0821 divided by 1073. That'll give us the 0.0303. So 0.0303, and that's going to be moles of H2O. Okay. Any questions on that? All right, next what we're gonna do oh, I'm an idiot. I'm sorry, guys, I made a mistake. Because we're not using the final pressure, we have to find the change in pressure. It's gonna be 6.14 because 2.67 is the amount that was not reacted. We have to talk about the amount that was reacted. I'm so sorry. Does that make sense, guys? So we started off with how much H2O did we started? Remember, we started with 8281 ATM in the beginning. This is our initial. But then we ended up with 2.67 ATM. So what matters for how much was used is the change, not the final value. I'm so sorry, guys. Mr. O is still waking up. So it has to be 6.14 because that's the amount that was actually used. I'm so sorry. Will you guys forgive me? Please forgive me. I appreciate that. No homework for the rest of the year? Dude, I should be giving you more homework to make up for my mistake.
Oh.
Because I want you guys to do better. And so it's a gift to you. So yeah, you'll get 0.0697. I'm so sorry, guys. Just to reiterate, we use 6.14 because that's the amount that was used in order to get to the equilibrium, not the final value. I'm sorry. I was looking at it and it's like, kind of doesn't make sense. Okay, so from here, it's very simple. All we need to do is set up a simple dimensional analysis. We're going to convert from moles of H2O to moles of carbon. What's the ratio? Yeah, 1 to 1. The moles of H2O will cancel out. And then we just need to convert using the molar mass. So 1 mole of carbon is 12 grams carbon. And then so we just need to do 0.0697 times 12. If I pull out my calculator, 0.0697 times 12, that'll get us. So the amount of carbon that we need to reach equilibrium is 0.8364 grams of carbon. So that's part B. So just to kind of recap what happened, we used the ideal gas law to find out how many moles of H2O were used. Okay, we used 6.14. Our final is 2.67, but the amount that we used was 6.14. We plug that into the ideal gas law, and then once we get our moles of H2O, we can use stoichiometry and molar mass to convert to the grams of carbon. Okay, make sense? All right, let's move on to part C and D. This should be pretty quick. I'm gonna try to. Okay, so what is the total pressure in the vessel? This one's really easy. The total pressure in the vessel is just going to be you just need to add the partial pressure of H2O, the partial pressure of CO, and the partial pressure of H2. Just add up all of the partial pressures. That should give you 14.95 ATM. If you guys don't trust me, which I don't blame you, you guys can check my answer. But the equilibrium pressures for all three of the gases, that's going to give us the total pressure. Okay, make sense? All right, let's get through this quick. I just want to get you guys out of here. So KP, so the new K, so at 25 degrees Celsius, the KP is going to be 1.7 times 10 to the negative 21. So let's just compare the numbers that we have. We said when the temperature is 800 degrees Celsius, the KP is equal to 14.1. Okay, but here, when the temperature is 25 degrees Celsius, the Kp is equal to 1.7 times 10 to the negative 21. Is the reaction exo or endothermic? So let's take a look at these changes. Here, did temperature increase or decrease? Decrease. Right, going from 800 to 25. And then if the temperature decreases, what happened to the Kp? Did it increase or decrease? Yeah, it decreased a lot, right? So temperature decreases, the equilibrium or the Kp decreased. So if the Kp decreases, does that mean we have more reactants or do we have more product? Remember, the Kp formula is product concentration divided by reactant concentration. If it's times 10 to the negative 21, is the numerator bigger or the denominator bigger? The denominator is bigger, right? Because if Kp is less than 1, we have more reactant. And here we have a lot more reactant. So if Kp went down to that means we have more reactants. Make sense? So if we have more reactants now, did the equilibrium shift to the left or to the right? Yeah, shifted left. I know so many different things going on, right? So if the equilibrium shifted left when the temperature went down, does that mean heat is a reactant or a product? No, it's gonna be a reactant. Yeah, heat is a reactant because when the temperature goes down, we created more reactant, right? You need more reactant to balance out the change, right? So heat is going to be a reactant. If heat is a reactant, is it endo or exothermic? It's endothermic, yeah. Yeah, so in your free time, make sure I know I went through this quick for the sake of time. Please go back to this and check it out because I think it'll make more sense if you have some time to digest it. Okay, last part. To produce maximum amount of CO and H2 at equilibrium, should the pressure be increased or decreased? I'll just tell you guys, you want to decrease the pressure. Okay, you want to decrease the pressure because you want it to shift to the product. Alrighty, guys. Sorry for the end where I had to rush everything. That was a lot of stuff. Make sure you guys look back at the video. If you guys have any questions, you want to check anything with me, please feel free to do that. And this will be posted online.